Good evening and welcome to Monday Night Calculus. My name is Curtis Brown and I am joined once again by Steve Kokoska and Tom Dick. I'm really excited to have you guys here this evening. You will note that I am also logged in and being the host tonight, so we don't have our wonderful Allison helping us out as she normally does, but I'm going to do my best to both manage the chat and try to manage these two guys as we get through some content. So Steve, I'll let you take it away.
All right. Thank you very much, Curtis. I'm going to try to share my screen here. Hopefully the technology is working tonight. Let's give it a shot. Can you see that?
Yep, looks good.
All right. I'm going to try to make it just a fuzz bigger if I can. How about that?
Looks awesome.
Beautiful. Okay. Well, tonight we're going to talk about implicit functions and derivatives. Derivatives are functions that are defined implicitly. And as usual, we start out with the skills and enduring understandings and learning objectives and the essential knowledge statements that are from the AP Calculus CED, and we hope that that will help some of the teachers out there. So for background tonight, Curtis, I really only have one item, and that means we have to know a little bit about differentiation rules tonight. And we have to recall especially the chain rule. That's going to be very important for us. So give me just a couple of seconds, Curtis, to kind of lead up to this idea. And then we're going to work lots of problems. And Tom has some really cool, I think, technology. So here's a brief introduction. You know that most of the functions that we deal with, Curtis, in AP Calculus, the variable y is usually expressed explicitly as a function of x. So, for example, we're used to seeing functions like this. For example, a polynomial over here. This one, y is equal to x squared log x. And again, where y is all alone on one side of the equation, and on the right-hand side, all we have over there are functions of x. Excuse me. Well, it turns out that sometimes, Curtis, functions are defined implicitly. They're sort of embedded into an equation involving the variables x and y. And here are just a couple of examples. So this one might look a little familiar. This one here, x squared plus y squared is equal to 16. I don't have y isolated all alone on one side of the equation. But there might be at least one, maybe two or more functions sort of embedded or defined implicitly there. And here's another one, x cubed plus y cubed is equal to 6xy. Now, in some cases, if we're given an expression like this, we can solve for y as a function of x. So, for example, let's take a look at this one here. We recognize that as the equation of a circle that's centered at the origin and that has radius 4. And we can actually turn around and solve that for y in terms of x. And if we think about the positive or the negative square root, we can actually think about this circle as being comprised of two different functions. The top half of the circle and the bottom half of the circle. Now, I should note, and maybe this isn't said enough, that's not the only, or these are not the only two functions that we could define or that we could get out of this expression defined implicitly. All right, sorry, Curtis, got to check with you.
Okay.
When we define a function, not only do we want the expression like this, but what other piece is also part of that definition of the function? Do you remember? There's one other little thing we need to know before we actually have that strict definition of the function. What is it? We've got
It's domain.
Beautiful.
Would be pretty important.
Gotta know the domain, sure. And so if we think about the domain, of course, we could split this up into many different other sorts of functions, but those are the two maybe the most common that we think about. So let's take a quick look at this other one. This expression actually has a special name. It's called the folium of Descartes. I'm sorry, I think there's a missing accent in there somewhere. I actually tried to solve this expression explicitly for y in terms of x. I actually used Mathematica to try to do this. I'm not sure what the TI-Nspire does with this, but Tom might be able to show us. This is what the graph of this expression looks like, and this is what I got in solving for y explicitly. Now, that expression clearly cannot give us that entire curve because that curve is not the graph of a function.
Right.
But it gives us a piece of it. And as a challenge, we'll just ask people out there to think about that, and maybe they could give that to their class tomorrow morning to try to figure out, well, what is the domain of this expression? And what piece of that graph do we really get if we try to plug that into our calculator and get an expression? Now, here's a way that I can break this folium of Descartes up into 3 separate functions. This is just one way, so that if I put all of those pieces together, I get that graph on the previous page. But here are 3 separate functions sort of defined implicitly by this expression. So this means that if f is a function defined implicitly, then this equation right here has to be true for all values of x in the domain of my function f. Well, you know what we're trying to do here is to find the derivative of this function f, and it seems like it can't be done because how the heck are we going to solve some of these expressions explicitly? But there is a really slick way to do this. So the problem is I'd like to find an expression for the derivative y prime, and it turns out that we don't need to solve for y in terms of x in order to find that derivative. We're going to use this method called implicit differentiation. And how do you do this? Well, I'll put a little star next to this, and then I'll expound on this just a little bit more. Basically, all we do is we differentiate both sides of the expression with respect to x, and then simply solve for y prime. So here's a little bit more delineated step-by-step procedure, and then we'll solve, or we'll try to take a look at several problems. So we have to think of y equal to f of x. We have to think of y as a function of x. And when we differentiate implicitly, we take the derivative of both sides of the equation with respect to x. So we have to think of y as a function of x. So that means that we need to use the chain rule to find the derivative of any expression that involves y. I'm just going to kind of underline this part of 3 because this is kind of weird in implicit differentiation, at least I think it is. When we solve for dy dx, when we solve for y prime, often the expression involves both x's and y's, and that's very different from a lot of the problems that students who are listening, you may have been doing up until this point. Okay, thanks for putting up with that, Curtis. Here we go. I'm going to try a couple. We'll get to some technology. Let's go back to this first problem that I introduced just a couple of minutes ago. This equation x squared plus y squared equals 16. And let's see if we can find y prime. And once we do that, let's see if we can find an equation of the line tangent to that circle at the point -3 square root of 7 jeepers. I forgot to check this. Does that lie on that circle? Yes, I think it does. 9 plus 7. Yeah, we're okay there. Good. Okay. So I start out in part A. I have to take the derivative of both sides. Derivative of 16 is easy. Derivative of a constant with respect to x, that's 0. How do I take the derivative of a sum? Well, the derivative of sum is the sum of the derivatives. Here we go. I take the derivative of this expression. That's just 2x. She's nice to have the technology working again, you know it?
Yeah, it sure is.
Take the derivative of y squared. We think of y as a function of x. So we use the power rule first. 2 times y to the first power times the derivative of the inner function, dy dx. I'm going to slip into this in a minute or two, Curtis, but I'm often asked this about the AP Calculus exam. Does it matter? Can students use that notation, or can they use simply y prime? And the truth is you can use either. I think y prime is a little bit easier to use, but I think that sometimes leads to some more, not arithmetic errors, but simplification errors.
Yeah, I can see that happen.
Can you see that? Sometimes the prime goes missing. Sometimes it's mistaken for a 1. So I'm torn between which one to use here.
Yeah, I can see that.
So, all right, I'm going to solve for dy dx. I'm going to divide both sides by 2. And I think if I did everything correctly, I get, oops, I'm sorry about that. I get a minus x over y, a perfect example of a derivative here found implicitly that involves both the variables x and y. That represents the slope for any of the functions defined implicitly. So at this point, minus 3, 7, I want to find the equation of the tangent line. Well, this is kind of weird notation here. I should probably write this a little bit better. Maybe I'll correct that tomorrow for you, Curtis. Maybe I should write that down there as a subscript. But I want to find the derivative where xy is equal to minus 3 square root of 7. So all I do is plug in x equal minus 3, y equal to square root of 7. I think I got a couple of negative signs there that cancel out. And there's the slope of the tangent line. So here's an equation of the tangent line. So y minus y1 is equal to the slope times x minus x1. Again, I'm often asked this question, can you leave an equation of a tangent line in that form? Absolutely, unless something more specific is asked for. I went on to simplify this just a little bit, and there we go. And that's kind of cool. So let me make a couple of notes about this, maybe even draw a graph, because you know I want to check this. Here's a challenge, another challenge for your students tomorrow morning. We already know here, we found the derivative, what was it, y prime was equal to minus x over y. Well, what I would challenge you to do is to find the derivative of y using that expression and see if you can reconcile this, see if you get the same answer over here as we did using implicit differentiation. So the expression for dy dx gives the derivative in terms of both x and y in this case. And again, I want to remind you that this is correct for every function y that's defined implicitly. That's kind of cool, I think. And here's a graph just to check everything, Curtis. I just wanted to make sure that this really worked. So here's a graph of the circle in blue. If you can see the colors, that's kind of cool. Here's my point on the circle. And I graphed the tangent line, and son of a gun, it does indeed look tangent to the circle at that point. I'm feeling pretty good about this. I think we did that correctly. So that's a good first way, a good first problem to try. I'm going to try one more, I think. And then I'm going to hand it over to Tom for some work with technology. Let me see what I can do here. What I tried to do, by the way, Curtis, is I tried to pick out some problems going back through the years here in AP Calculus, some good representative problems of the types of problems that they ask. So you'll see that in some of my examples, and you'll see that in some of the problems that we assign for homework. By the way, are we collecting homework tonight, Curtis?
I mean, I hope not, because I didn't do mine.
Okay. All right.
I did post the teacher notes and the student document to the description, though. So if anybody wants to download and follow along, it's down in the YouTube description.
Okay, very cool. Very cool. Okay, so here we go. I want to find dy dx if y is a function defined implicitly by that expression. Okay, jeepers, I don't know if I could solve that for y in terms of x. So I'm going to take the derivative of both sides. The right-hand side is easy. The derivative of 10 is 0. How do I take the derivative of the left-hand side? Well, the derivative of x cubed is easy. That's 3x squared. I've actually got to take the derivative of both of those underlined terms, both of these, using the product rule. So I tried to separate those in brackets so that you could see that a little bit more clearly. Here we go. Derivative of this. X squared times the derivative of y plus the derivative of x squared times y. Minus, there's that minus sign. I chose to bring that outside here. X times the derivative of y squared plus the derivative of x times y squared. Okay. All right, let's see what I got here. Derivative of y, just y prime. That looks good. Derivative of x squared, 2x. Derivative of y squared, 2y. Don't forget the chain rule, y prime. Derivative of x is 1, and there's my y squared. Yikes. So when I get that far, after maybe a little bit of simplification, the standard technique here now is to sort of gather all the terms that involve y prime or dy dx, gather all those terms to one side of the equation. So I brought them all to the left-hand side. Bring everything else to the right-hand side. Do a little bit of factoring on the left, take out that y prime, and then finally divide. And there's an expression for the derivative of all functions y defined implicitly by that expression, and that's very cool. Now, there might be a little bit more simplification in there, but I didn't see it rather quickly, so I left it like that. And here's something kind of cool that we can take a look at, and Tom may be able to do a little bit better at this with technology, but here's actually a graph of this expression. And I think I can see probably, how many functions can you see in there, Curtis? Can you see, let's see, I think I can probably see at least 4 in there, huh?
Yeah, something like that. I think
There's
about
one
4.
up here. Yeah, there's one up here. There's one down there. We can probably break this and a function up there and a function down there. And very cool. So one thing one might think about is, it doesn't seem like, anyway, unless it's off the graph, so this is another challenge question. It doesn't seem like there's any part of the graph showing for x in between about 0 and 3, maybe. So one wonders what's going on there, and we might leave that as sort of an open question, something for you to think about tomorrow before your AP Calculus class begins. Tom, a little bit of technology, is that correct?
Sure. Yeah.
Okay.
Give that a shot.
All right. I'm going to stop my share. There you go, boss.
Okay. Let me see if I can pull up something to share here. You guys can give me some feedback if that's showing up. All right. It's a TI-Nspire screen with Monday Night Calculus on it.
Looks good.
So what I have here, this is the TI-Nspire CAS. I'm going to do some things with both TI-Nspire and the TI-84. The thing I'm going to show you with the TI-Nspire CAS, first of all, graphing implicit relations. You can do that whether or not you have a computer algebra system. Okay. So let's go ahead and take a look at a graph. And I'm going to go back to an example that Steve had looked at just a little bit ago, and that was I think it was x cubed plus y cubed equals 6xy.
Sounds good.
That matches up with what we had before. Okay, well, let's take a look at how we could graph that. So I'm going to go to graph entry edit, and instead of function, I'm going to go down to relation. And you see it says REL1 of XY. And so that's a relation. And that can be any equation in terms of X and Y. So I'm just going to go ahead and enter the equation that Steve was working with earlier. I think it was x cubed plus y cubed equals 6 times x times y, and we'll enter that. That's interesting. That blue line comes across the screen there. I'm not sure what that is, but boom,
boy,
there it is.
Nice.
And I think that's matching up really nicely with the graph that Steve had generated with his software. And we haven't given away Steve's challenge question, which was he presented an explicit function that did not actually match any of the graphs he showed. And it's going to be some subset of this, but he's wondering exactly which subset it is. So we still have that open. So for an actual...
Looking forward to hearing that answer too.
Hey, Tom, is it possible, maybe you're going to do this, I apologize. Is it possible to use a CAS machine to solve for y in terms of x in that expression?
Yes, I believe so.
Okay,
So we
cool.
can give it a shot
Okay,
and see what it gives us. Also, on a numerical, even if you don't have the CAS,
yes,
I believe like on an implicit relationship like this, we can still look at the slope or the
okay,
value of dy dx at any point on the curve. So let's take a quick look at that. I'm going to bring up the menu again. And let's go down to number 6 here. We're going to analyze the graph, and I see dy dx. That looks good. Let's go down to dy dx. Whoops, I hit the wrong key. My apologies. So let's try that again. Analyze graph. I overshot by 1. I'm just going to hit the number 6 because that is dy dx. All right, so dy dx, it says the position. I can point to the curve, put a point on it, and that is telling me the slope at that point. Let me move that numerical value. Let's see, maybe I can move it. Well, I'll leave it there. Oh, there we go. Okay. A little bit sluggish here. Let's see. Anyways, as I move the point along the curve, we can see the slope is updating. And visually, this is making sense. It's looking like I've got a slope of a little less than -1 here. Well, when I say less in magnitude, so we should be getting slope close to 0 near this flat place.
looks like it. Yep.
Yeah. We should expect some kind of funky stuff at the origin. If you look at that curve, wow, there's actually multiple tangent lines you could draw there because there's different pieces of explicit functions all meeting at that one point. So as I move there, I see, let's see, these are slopes that are close to 0. Oh, but here's some large positive slopes. That's because very nearby I'm on that loop here.
Yeah.
Okay. But we can see we can move this point along the curve and see any of these numerical slope values. And that's going to work on the TI-Nspire machines, both CAS and non-CAS. Now, if you do have CAS available, there are some interesting things you can do. So we'll go to another page here. This is just a calculator page. Let's see, Steve, you'd asked about, could we actually solve that equation?
Yeah, I wonder if the CAS can do that.
So let's give it a shot.
Okay.
Then we can hold on to our hats and see what happens. I'm going to try something here. I've already labeled that equation rel1 of x.
Oh, yeah.
So
Okay.
let me go ahead and just put in rel1 of xy.
Okay.
And that is an equation. And
Right.
I want to solve that equation for y.
Gotcha.
And let's see what we get. Oh my gosh.
That's right.
Interesting stuff. And
Yeah,
this is, I think the thing that is most surprising, and it is to me at least, is when you see that inverse trigonometric function popping up.
Yeah.
In an interesting way. It's like making sense out of, wow, what is this thing doing? Also, I'm seeing this little warning sign.
Hey,
yes, go ahead, Curtis.
I was just going to say, Tom, type it in as you had it, rather than calling it relation 1 xy. Type it in as it was. So type in solve x cubed plus y cubed equals 6xy. Solve it for y. It's interesting that you get it a little bit different solution here. I wasn't expecting to see what you got just now, because I was doing this on my handheld while you were doing it earlier. I got something a little bit different.
Okay, so this is that equation as we typed it in before, x
Right.
cubed plus y
Right.
cubed equals 6 times x times y.
Right.
And we're indicating we'd like to solve for y.
Yeah. Oh, you know what? I may have had a typo then.
Okay, yeah, I think it's coming up with the same thing.
Good. Good.
Kind of
Okay.
reasoning through what's going on here, though, is kind of wild.
Yeah.
It is pretty wild.
Well, you might say, well, how could there possibly be an inverse trig function? Notice that that inverse trig function is on the inside of a set of parentheses where there's another trig function being taken of that. So if we think about it, this is giving us, in some sense, an angle that depends on x, but then this trig function will give us back a real value. So this is resolving in some nice way.
Yeah.
Yeah.
But it's surprising because it looks nothing like the one you had, Steve. So
That's
there's
right.
a lot of
Yeah.
different functions
Yeah.
that could fit pieces of that graph. Okay.
And there was another question that came up in
sure.
the chat, Tom, just while we've got you kind of interrupted here. There about whether there are functions that cannot be used in graphing a relation. To answer that question, one, I think apart from certain, I guess, powers of polynomial type expressions, so you know, really high powers raising y or x to really high numbers. Other than that, I don't know of any limitations off the top of my head to the things that can be used, or to the functions that can be used in graphing a relation.
I would respond to that. I don't know of any restrictions either, except that you might be able to come up with some crazy expression or relation in which there are no solutions.
Sure.
Okay. So the solution would be, well, maybe 0 or just the origin, or essentially nothing.
Yeah. That's possible too, Steve, for sure. Right.
Okay. Well, the other thing I was going to show is how you can do it. If you do have a CAS on board,
okay,
you can do an implicit derivative symbolically. So I'm going to go to the calculus menu here, and I don't see implicit differentiation right off the bat, but let's just keep scrolling down. Differential. Wait, I overshot, but I'm just going to go up. There it is, implicit differentiation. So let's go ahead and hit enter on that. And you could just type this IMP-DIF in if you remember that's the shorthand notation for implicit differentiation. And so for this, we'll put in that same relation. And now you indicate the independent variable. What are you taking the derivative with respect to? And the dependent variable. In this case, it'd be y. So you're really indicating both the dy over the dx because it's in terms of x and y. And hopefully we'll get something here. Very nice. Now this one is not hard to do by hand with implicit differentiation. So I'd encourage people. I don't think you actually did this one with an implicit derivative, Steve. So we'll leave it to people maybe to jot this down and check it out for themselves, and then they worked it out by hand if it came out to be the same way.
Very cool.
Hey, Tom.
Yeah.
There was another question that was asked in the chat. Kathleen asks, what is to the right of or in your solution, and why?
Oh, yes, that's a good point.
That's
also, I think
if you arrow up, I think you can copy that and paste it down where you can read it, or you may be able to just right arrow.
There. So I just pasted it down. And it looks like
There you
a,
go. Now you can
oh,
see the rest. There you can
yeah,
see the
so
rest of
it's,
that expression. So it's another chunk of this.
So Tom, would you do me a favor? Would you arrow over on that line slowly? Because it almost looks to me like there are 3 expressions for y there.
oh, I think you're quite right, Steve. I think there's 3 different
Are you sure? I
solutions
think I
here.
only saw 2.
Well, I don't know. There's
Well, the
one.
reason I say that is one of them had a pi over 6
Yeah.
inside the parentheses, and I'm seeing on the tail end of this one a pi over 3.
Yep, there's the second one. Okay, keep going.
Oh,
Yep.
So there's one there. 2 of them have.
oh, you're right, because I saw the
Yeah,
sign.
there's at
I
least
did
3
not see
unless
the arrow
if
continue.
this,
That's
unless
right.
there's another one besides this one. No, that's it. I think there's 3 different
Good
ones.
point.
Yeah.
And actually, I won't do this right here. But what would be cute to try is graphing each of these 3
Yeah.
as a regular function.
Yep.
And see if their graphs, how the graphs look compared to that original loop-de-loop. I'm going to go up here a bit too and take a look at this warning sign.
Yeah.
Let's see. An undefined parameter, the input. Not sure what that's referring
May
to.
not be
honest.
valid for all possible parameter values.
Huh.
Well, to me, I mean, naively, that means to me there might be some value of x where the derivative, or pardon me, where y is not defined.
Right.
Yes,
Yeah.
exactly. That's
Possibly.
you pegged it,
Possibly.
Steve.
I
Yeah.
don't know.
We had it solve this expression in terms of x and y for
Right.
y.
Mhm.
It says, well, I don't know what x is. So some of the time, depending on the value of x,
Sure.
we may run, some of these things might not make sense.
Right.
Very
That's
good
also
point.
possible.
Yeah.
For sure.
Okay. So Steve, I'm gonna
Okay.
use your guidance here. I can go ahead and show something on the 84 right now, or if you'd like to pick up and I can come back to it later, I can do that.
How about if I do one more example and then you could do the second derivative and the 84? How about that?
Yes, sounds
Does
good.
sound okay? All right.
Yeah,
Very
okay.
good. Okay.
So I'll stop my share.
Okay. All righty. Beautiful. Excellent. How's that, Curtis? Okay.
Looks great.
Okay, so if those of you who have a TI-Nspire might try to produce this curve here at the bottom of this page, this one that we just took a look at, that'd be kind of cool to see if you could produce that, given what Tom showed you. Well, let me try one more, extend this just a little bit, and then I'll hand it back to Tom again in a minute. So here we have another expression. Be careful. This is an x to the 4th plus x squared equals 16. So this isn't the graph of a circle. Not sure what this is the graph of, what this looks like. But this time what I want to do is I want to find y double prime. Now there are a couple of ways to do this. I'll show you a way and suggest another way that you might do this, which might make it a little bit easier. Again, you've got a lot to do before class tomorrow. Here we go. I'm going to take the derivative of both sides with respect to x. Pretty easy. 4x cubed, 2y times the derivative of the inner function. I'm going to turn around and solve this for y prime. There we go. I'm part of the way there. Now, in this problem, what I really want to do is I want to find y double prime. And so what I can do and what I did do in this problem is I found the derivative of this right-hand side of both sides once again with respect to x. But some people would find it easier to do the following, is to rewrite this as y prime times y is equal to minus 2x cubed. And now take the derivative of both sides, again, with respect to x. You have to make sure you use the product rule on the left-hand side. But by doing it this way, you don't have to use the quotient rule, which might be a little bit more cumbersome for some people. So here we go. I'm going to try this with the quotient rule. Derivative of the left-hand side, there's my y double prime. Derivative of the right-hand side. What I chose to do, Curtis, is to bring this minus sign out in front. Now I'm going to apply the quotient rule. I bring the denominator up. There it is, derivative of the numerator minus the numerator times the derivative of the denominator, denominator squared. Okay, a little bit of simplification. I see a y prime in there. So what do I do now? I've got y double prime in terms of x and y prime. So frequently, I would say these questions on the AP Calculus exam, if you see one like this, especially on the multiple choice portion, would want y double prime in terms of just x's and y's. And so what we've got to do is we've got to take this expression for y prime and substitute in here. So I did that. And in the interest of saving a little bit of time, there's 3 dots in here, Curtis, I did a little bit of simplification and I arrived at that expression for y double prime. Pretty cool. Pretty cool. So we can actually take implicit differentiation another step further here to find y double prime, perhaps even to tell us a little something about concavity. Tom, can I turn it back over to you? I'll take that as a yes or a no.
Sorry, I had myself on mute there. Go ahead. Yes.
Okay, there you go.
Okay, sorry about that. Okay. All right, I'm going to do a couple of things here. Let me go back to the Inspire example we had.
Okay.
And I'm going to, let's see, let me, there we go. I'm on a fresh line and I'm just going to do another implicit derivative.
Okay.
Of the equation that you had, I think. So
Okay,
that was
good.
x to the 4th
Yep.
plus y squared
Yes, sir.
equals 16, I believe.
Perfect.
And I want to do an implicit derivative. So we'll take the derivative with respect to x. We're doing dy dx. So I'll put in the y for the dependent variable.
Okay.
But an optional argument here would be if you actually want the second derivative implicitly, you can just put the order in here.
Wow.
So it'll go directly to the second derivative.
Okay.
Now, this doesn't look identical to what you had, Steve, but it is actually equivalent. It's just a little algebraic. They've broken it into 2 different fractions. I think you had a y cubed, but one of your terms had a y squared in it, and that's the cancellation that we're seeing there. Okay.
Wow, that's pretty cool.
All right. Okay.
That's really cool.
So I did want to show folks how to do, I think sometimes people do a double take, but the TI-84, very nice machine, but it doesn't have CAS on it. Okay. And so anything we are doing with calculus there, we'll be dealing with numerical approximations. We've got our numerical derivative. We've got a numerical definite integral function that we can do. And even with that definite integral function, we can plot integral functions, like using the fundamental theorem. But there is a way to do implicit differentiation at a point. And I just want to illustrate how you can do that on the TI-84.
Okay.
Now, I'm still on the Inspire here, but what I'm going to do is just kind of run through the basic steps you need to do on the 84. So if you've got an expression in terms of x and y, one of these relations, and you want to find the value of the derivative at a specific point, x, y, so let's say, and so this a and b are the specific coordinates of that point. What you need to do is, first of all, if your relation is not already this way, you want to express your relation by getting all the variables on the one side of the equation. So what you'll end up with is something in terms of x and y equals a constant. And a constant's very often, when people are moving everything over to one side, that constant is a lot of times 0. Okay, but it doesn't have to be. Then the specific coordinate you're interested in finding the derivative value at, go ahead and store those coordinates in x and y. And then what you're going to do is calculate, using that expression in x and y, you can take the numerical derivative of that with respect to x, where x equals a, take the derivative with respect to y, where y equals b, and then you'll take the negative quotient of those two quantities. Seems really strange, but this actually works out to be dy dx at that specific point. So let's go ahead and illustrate this and see if it actually works.
Okay.
I'm going to go back to this example here that you started with.
Okay.
And what I'm interested in is, I think the point 3, 3 is on this curve. Let's just do a quick reality check here. So 3 cubed is 27, plus 3 cubed is another 27, would be 54. And that's 6 times 3 times 3.
Okay.
So 3, 3, well, we can kind of see, maybe I can even move this point up to there. Am I getting close to 3, 3? Oh, I'm not sure.
That's pretty good.
Somewhere up. Yeah, it looks like it. Really close up here.
Yep.
In fact, I'm not exactly there, but it looks to me like the slope there, this would make sense. It looks like the slope's about -1 there.
Is there a way, Tom, to display the coordinates of that point?
Yeah, I think so. Let's see. Or, another thing I could do here, let me try this.
Okay.
Let's just do under geometry.
Okay.
And I'm going to do a point by coordinate.
Okay.
And so I'm just going to put in 3, 3.
Okay.
All right. And then let's see. And yeah, well, we have an expression for the derivative at that point. So we could take a quick look at that, see what it should be.
Okay.
That was up here, I think. Here it is, right here. It's x squared minus 2. Well, so what would this be equal to if x and y were both 3? See, I think I'd have 9 minus 6 is 3 over 6 minus 9, which is -3. So it's going to be a slope of -1 right there at 3.
Okay.
All right, so how would we do the derivative of this on the 84? Well, let me switch over to the TI-84.
Okay.
And okay. So, as a handy place to put that expression, we could actually use our y1 from the y equals menu. So here, what I'm going to do is put in the x cubed plus y cubed.
Whoops, hang on.
Oh, thank you.
Yep.
That's never happened to me before.
Is that right?
No.
You're a better man than me.
No. Yeah. Now, remember what we said is if you're doing this on 84, you want your relation with all the variables on one side.
Okay.
So I'm going to bring the 6xy. I'm going to subtract that from both sides.
Okay.
So it would be x cubed plus y cubed minus 6xy equals 0.
Okay.
That would be another way to write the late. So I'm putting the expression that had all the variables in it into y1. And now I'm going to go to my calculator screen. And let's see, the point we were interested in was 3, 3.
Right.
So I'm going to store 3 into x.
Into A.
And I'll store
Into
3
A.
into y.
Oh, I see. I think.
Yeah. So you store the 2 separate coordinates of the point
Okay.
you're interested in into the x and y values.
Okay.
And now I'm going to calculate the, first of all, I'll get a negative. I want the derivative of y1 with respect to x at x equal 3. Remember, y1 actually is this expression in both x and y. Okay, so let me get my y1. Oh, I messed up again here. Sorry about that. I need the derivative, right? So let's get the numerical derivative up there. And we'll take the derivative with respect to x of my y1. And we'll do that at x equals 3.
Oops.
So we'll take the negative of that derivative and we'll divide by the derivative of that same expression with respect to y. Now notice when I type in y here, you'll see the y pop up at the back part of that expression where it has a little square equal to something. So notice this y equals popped up here.
Yep.
And so we'll go to variables again. And this was also where y equals 3. That's now, those could be 2 different coordinates, right? But the point we were interested in was this one. And finally, after all that, so let's see, we had figured out before that the implicit derivative at that point should be -1.
Right.
So let's see if the TI-84 is able to calculate that same thing. Boom.
How about that?
There it is. Great. Yeah.
Very
So
cool.
it's an interesting technique. If people use that Leibniz notation and think about it, you can kind of see where there's a dy dx coming out of this. But it's I'll say up front, the way we presented it here is a little bit of a black box, but I would propose it's a neat way that if you're doing implicit differentiation by hand, is a way of checking yourself, is taking a point, even if you're not given a specific point, find a specific point on the curve, find out what the slope should be from your equation for the implicit derivative, and then check it out using the numerical tools on the 84.
So Tom, one question before you leave this. Certainly,
Sure.
it's calculating this all numerically. And the -1 came back here, which almost makes me think, oh, well, that's a cast response. But certainly some of the answers here, might not be exact if we did it by hand, right?
Right. So if you came up with something like a 0.33333, you might be thinking, okay, that's probably 1/3.
Third, yeah. Right. Okay. Okay. That's still cool, though. Still very cool.
It is. Yeah. It's I was kind of really surprised the first time I saw that you could do this on the 84. So
Very
neat
neat.
thing. All right. I'll stop my share and turn it back over
Hey,
to you.
Tom.
Yes,
We
sir.
just got an interesting question on the, I've been chatting with Wanda Burns a little bit on the capability of what you can graph implicitly on Inspire and not. And we got an interesting question from Bradley with Stokes theorem, doing a problem with Stokes theorem. Is that in the capability here, or did I miss something?
Boy, I'd have to think about that a little bit. Stokes theorem is something that's usually in vector calculus.
Yeah.
Sure.
But you know, there is
Well,
a surface plotter on the Inspire, and so
Sure.
Yeah.
the thing about the surface plotter is I'm not sure you can do directly just on the Inspire on the just the y equal f of x graphing. You do things like a definite integral right on the graphic screen. I'm
Right.
not sure you can do a multiple integral directly on a graphic screen on the Inspire. I'm pretty certain
Okay.
you can't do that.
Okay.
And that's kind of what you would like to be able to do with something like Stokes theorem, I think.
Okay,
Ring
that
me
makes
in,
sense.
Steve, if you've different
No,
take on that.
Absolutely. Yeah. I mean, I'm going to take a wild stab here that the only way you might be able to do that on the calculator is if the function inside the double integral can be separated into a function of x and a function of y.
Yeah, that might. Yeah,
That
that might.
might work.
might
I'm not sure. I'm not
Right.
sure. And of
Good
course,
point.
your bounds would have to be reasonable too. But so there may be
Right.
special cases, but I'm not sure.
Yep. I think the function of x, function of y piece is probably it's a good thought. I was just thinking about that in the same way we were trying to, Wanda and I were trying to do different kinds of implicit graphs. And I think that function of x, function of y thing does help the implicit grapher manage some of those more complicated functions.
Okay, well, I'm going to try a couple more, Curtis, before we call it a night, if it's okay.
Yeah, I think that's a great idea. We've got
Okay.
just a few minutes here to look at a couple more things.
It's okay. So we did assign some problems for homework, but I'm going to take a
Well,
look.
you did. I hope some teachers out there did too.
Okay. Well, I'm gonna take a look at two of my favorites here. So I had a couple here where there were some pretty standard sort of problems where we are given an expression where y is defined implicitly, and I ask you to find y prime. And again, what I try to do is to draw from a variety of problems that I've seen recently on the AP Calculus exam. So I'm not going to take a look at these. We will, of course, post all of these answers, or they may already be there. So there's B, here's C. This is an interesting one, which has a trig function in it. I thought D is also a little bit different. It has a trig function or two, but it also has in the argument here a product. So you have to be very careful there as you take the derivative of the inner function. The derivative of that inner function is the derivative of a product, and you still have to remember the chain rule. So that's a good problem, I think, to practice on. Did I have an E? Yes, E had some logs and some exponentials in there. Also, I think an excellent problem for practice by hand. But let's take a look at number two if we can, if we still have a little bit of time. I really like this one, and there's a great challenge question in here, Curtis. If I may ask you to stay alert for this one. Here we go. Let's consider the graph of this equation, y squared equals x cubed plus 3x squared. Now, it kind of looks like that I might be able to turn around and solve that for y explicitly. I mean, I can take the square root of both sides and I can get a plus and minus, and it seems like I can get two pieces here. But in this form, this curve has a special name. I'm going to butcher that, I think, but something like Turnhausen cubic. And the first thing I want to do is find an equation of the tangent line to this graph at that point. I think that point 2 square roots of 5 is actually on the curve. So this isn't too bad. I take the derivative of both sides. On the left-hand side, it's pretty straightforward. 2y times the derivative of the inner function y prime. The derivative of the right-hand side, well, it's really just a polynomial. That's pretty easy. 3x squared plus 6x. And now I want to solve for y prime, so I divide both sides by 2y, and there we go. I've got the expression for y prime. So I want to know the equation of the tangent line at that point, so I need to find the slope. So I'm going to let x equal 2 and y equal 2 square roots of 5. I know you can check me on this one, but I did a little bit of rationalization here, and it ended up with 6 square roots of 5 divided by 5. So here's an equation of the tangent line in two forms. Remember, again, you can leave it like this on the AP exam unless it's asked for in an explicit form, in some other kind of form. I wrote it in a more standard form, maybe like that. And here's a visualization. It's kind of tough to see that tangent line, but I'm feeling pretty good about this. This is kind of like the curve we had a minute ago, but kind of flipped a little bit. And the tangent line is up here at 2 square roots of 5. I feel pretty good about that. I think we found the right answer. But there's more here. Let's see if we can do this. Let's see if we can find the points on this graph where the tangent line is horizontal. Well, I'm going to cheat a little. I'm going to peek down here just a little bit, and I drew in a couple of horizontal lines where it looked like the tangent line was indeed horizontal. So one there and one there. So let's see. If I solve this, if I want to find out where the derivative is 0, what do I do? Well, if I want to make a fraction equal to 0, the only way to do that is to make the numerator equal to 0. So I'm going to set the numerator equal to 0, and I'm going to factor, and I get x equal -2 and x equals 0. I'm going to handle this case in a minute. That's a little bit more difficult for me. I'm not sure what to do there. We're going to have to issue that as a challenge question and come back in January and answer this one, I think, Curtis. When x is equal to -2, I'm going to go back and plug that into the original expression. I'm going to get y squared is 4, so I get 2 values of y. And so I get 2 points here where the tangent line is horizontal. And you know what? That seems to make sense. If I take a look at my graph, indeed, it looks like it's at 2, -2, 2, and -2, -2. It looks like the tangent line is horizontal there. I feel pretty good about that one. But now, Curtis, what do you do with this x equals 0? I got an x equals 0 out of this expression. What do I do there?
Well, Steve, I'm really glad you asked me to pay attention just a minute ago, because I was looking at this and I'm noticing that you have a division by y up there.
Yes, I do.
When x is equal to 0, it appears just based on the graph that y is also equal to 0, which gives me this some problems.
Well, very good. I'm very impressed. It certainly looks like at the origin 0, 0. First of all, it looks like the curve goes through the origin at 2 different times or places.
Right.
That's kind of weird. But it also looks for sure to me that the tangent line is not horizontal there.
Right.
Allow me, right? If I draw in a tangent line, at least on one side it looks there, another side it looks there. So it doesn't look horizontal.
Absolutely.
But I wonder how I would show that analytically. I mean, yeah, I can look at the graph and yeah, I believe that the tangent line is not horizontal. But what am I going to do to show that analytically to convince me on that AP calculus exam? I don't think we'd see one like this, but you might see one on my exam. So what am I going to do here? How am I going to show that the tangent line is not horizontal there? Or maybe a better question is, what is the slope of the tangent line at the origin? So we'll leave that as an open question. Maybe somebody will give us an approach to that before we sign off for tonight.
Yeah.
And we'll leave this as one other open question. I wonder if there are any places on this curve where the tangent line is vertical. I mean, it almost looks like there's a place over here, and I wonder how we would find that. And I don't know what's going on over here with this curve. I only drew it up to about x equal 4, but maybe there's another place or two way out to the right-hand side in quadrant 1 or quadrant 4. So we'll leave that as an open challenge too.
That's a good question.
I like that one. And let me just end with this one, because this is a great question for your students, teachers out there. This is a great question for them. This brings back really good memories for me, Curtis. This is one of the problems that I actually did in one of my very, very first College Board presentations as a consultant. Let's consider this graph of this equation. The square root of x plus the square root of y is equal to the square root of c, where of course c is greater than 0. And this one says, find the sum of the x and y intercepts of any tangent line to this graph. So as I read that initially, I think, well, maybe the sum is some function of c, something like that, and maybe there's a constant like the square root of 3 in there or something like that. This is a very cool problem, and we can actually do this with implicit differentiation. So I'll at least start this, and we'll leave maybe a little bit of this for teachers to finish up tomorrow. So I'm going to start with this expression. I'm going to find the derivative y prime implicitly. Little tricky here, 1 divided by 2 square roots of x, because remember, I have to think of this as x to the 1/2 and y to the 1/2. So 1/2 y to the minus 1/2 times the derivative of the inner function. It looks kind of funny, but that's just a constant, so the derivative over there is 0. I did a little simplification. There's the slope of the tangent line for any x and y on that curve. So what I did is, let's pick a point on that curve. So there it is, x0, y0. So there's x0, and over here is y0. So here's the equation of the tangent line. There it is, because there's the slope. And now I want to find the intercepts. How do you find the intercepts, Curtis? Are you still with me? I let x be equal to 0 so that I can find the y-intercept. I let y equal 0 so that I can find the x-intercept. And without revealing too much, I wonder what happens when you add those values together. And we'll leave that as sort of an open question, and you can take a peek at what we've posted on our Monday Night Calculus page.
I'll admit I don't have the answers pulled up here, so I'm gonna have to go take a peek
I like
at that, because I don't,
That's a
I
cool
didn't have
problem.
the solutions ready to go.
I think that if Tom had more time, I think that he could develop a nice dynamic TNS file on the TI-Nspire for this one, and
yeah,
that would be really cool.
That would be.
Thanks,
kind of
Curtis.
cool.
Thanks for putting up with that. That's a nice.
Well, no, that was good. That was really good. Thank you, Steve. Thank you, Tom, for your expertise this evening and for sharing everything. If you have been enjoying these sessions, we'd sure enjoy it if you'd hit that like button down there in the corner, and maybe even subscribe to the YouTube channel. Also, I just want to kind of point out again that we have posted all of these in this series, the Monday Night Calculus series for the fall. We've posted a teacher document and a student document for each one of those, as well as if you go back and watch these later on demand, or if you've stayed with us all the way through this evening live, I have PD certificates for the teachers out there, so you can email me at my email address. I think I put it in the chat just a moment ago, curtis@ti.com. And we will be back in the spring. So we'll be looking for email and Facebook posts around that. But we plan to have a good set of these videos, these live sessions ready to go for you in the spring. More teacher and student documents ready to go. Steve and Tom work really hard to make those things available to you. So hopefully you can use them with your students. Otherwise, I will wish everyone a great and happy end of the year and holiday season. So thank you for joining us, and we will see you in the new year.
Very good. Thanks, Chris.
Thanks.